This is fundamental problem 1 from chapter 19. The 60 kilogram wheel has a radius of gyration about its center O of 300 millimeters. If it is subjected to a couple moment of 3t squared, where t is in seconds, determine the angular velocity of the wheel when t is equal to 4 seconds, starting from rest. So, for this problem, we have rotation about a fixed axis, which is discussed on page 523. And we can use equation 19-13, which is on your equation sheet, but on your equation sheet, I brought the initial angular momentum over to the other side. Okay, the initial angular momentum is equal to 0 because we're starting from rest. So I have 0 plus the sum of the moments integrated with respect to t. So we have our couple moment of 3t squared. We're looking for the angular velocity when t is equal to 4, so we start at 0 seconds, the angular velocity is equal to 0, and we go to 4 seconds. And this is equal to the moment of inertia about O. Now, in order to do this, because they gave us the radius of gyration about O, we do the mass times the radius of gyration squared. So we have the mass of 60 times the radius of gyration is 0.3 squared. So this is the moment of inertia about point O. Then we multiply this by the angular velocity, and that's what we are looking for. So when I do the integral here, I'm integrating 3t squared with respect to t. I raise the power from 2 to 3, divide by the new power, and that just becomes t cubed, going from 0 to 4. That's 4 cubed, is equal to 60 times 0.3 squared times omega. Therefore, omega is equal to 4 cubed divided by 60 times 0.3 squared, and that gives us 11.85 radians per second, and that's the solution to fundamental problem 1. When you are taking your last exam, you may have to decide whether to use the equations from chapter 19 or the equations from chapter 18. So this is similar to when we had chapter 14 and chapter 15. So for chapter 19, for angular momentum, we are integrating with respect to time, whereas for work energy, we were integrating with respect to position. So if you are in chapter 18 or chapter 19, and you are given a function of t, then you probably want to be using the equations for chapter 19. Now, if you were in chapter 17, you could use the equations that we have here along with kinematics to solve this problem. Okay, but if you have to use conservation laws to solve this problem, if you have a function of t, you want to be using impulse momentum. Okay, and that concludes fundamental problem 1.